Yes, hello everyone. This is Dr. Bassam Alhamad, CHENG324 Process Modeling and Simulation, and we are going to have our third lecture today, lecture number 3. And in our third lecture for today, we will try to develop the model equations. So we are trying to develop the model equation for a CSTR reactor. So what is a CSTR? CSTR reactor is a continuous stirred tank reactor. And when we say continuous, because we have input and we have output, so it's a continuous process, and it's also a stirred reactor. That means there's a stirrer, and it is a tank, so that's the third T, third letter, and it is a reactor. So we have a CSTR tank, and in this CSTR tank it is very important to consider in the CSTR tank, okay, sorry for that. So for the CSTR tank, it's very important to know how does height change with time. Why? Because we don't want our process to overflow, and we also want to know how do the inputs react. So if I have A or B, and how do they react with each other, and then they produce, for example, A plus B produces C. So they produce a certain product C, and then you're collecting the product C here. So in other words, we want to know the concentration. How does concentration change with time? And when we talk about concentration, I have concentration of A, concentration of B, and concentration of C, which is leaving the reactor. So what do I have? I want to know how does height change with time. I want also to know how does the concentration, how does the concentration change with time? Well, in some another lecture, we are going to study how does the temperature also change with time. Why? Because temperature are key. They are key process variable for any reaction. So for example, if we have an exothermic reaction, the most popular thing, other than talking that it is the reaction rate will increase because of a kinetic or a thermodynamic point of view, for an exothermic reaction, what do you need to do? Usually you need to cool down the system. And if you have an endothermic reaction, endothermic, that means it takes in heat. That means it makes the process cooler. So what you are trying to do here, you will try to heat up the process. And we'll come to the details, but what I'm trying to say here is that we're trying to control the temperature of the reaction. So let's do it one by one. So we want a model equation that represents, how height changes with time. Sorry again for that. Still learning how to use this kind of software. Okay, so we want to know how does height change with time, which means dH by dt. We want to know how temperature changes with time, which is dt by dt. We want to know how does concentration change with time, which is dC by dt. Wow. Okay, that's beautiful. And if you just can recall, we said that in lecture number 2. The last lecture is that we can get how height changes with time from the overall mass balance equation. We can get this dC by dt from the components mass balance equation, and we can get how temperature changes with time from the energy balance equation. So let's start doing it. So I'm going to run a overall mass balance. So that is an overall mass balance equation. So the overall mass balance equation comes from the law of conservation, and this law of conservation says that mass cannot reproduce, it cannot be created. At the end of the day, if mass is going to be leaving at one part, it's going to appear in another place. Simply, you already have taken this. Accumulation is equal to input minus output. And in overall mass balance, you do have a generation and consumption term, but they simply cancel each other because what had been generated is also consumed for the overall mass balance equation. So we are not going to consider those terms. So we're just going to say accumulation is equal to input minus output. The others are going to be cancelled out. So let's continue. So how does mass change with time? Is the accumulation term is equal to input, which is the input flow rate, minus the output flow rate. And we know that mass is equal to density into volume. So we know that mass is equal to density into volume. And we have also said that this will be rho into volume. And in this case, my volume for a tank is the area of the tank. So the area of the tank, that means this cross-sectional area, multiply by the height of this tank. Multiply by the height of that tank. So this is area into height. I don't know why it always takes me up there. So that is rho area into height. Okay, beautiful. So I'm going to substitute here. That is rho A height by dt is equal to mass flow rate N. Okay, rather than writing that directly, if mass is equal to density into volume, which means mass flow rate is equal to density into volumetric flow rate. Beautiful. That is exactly the equation at the top here. And we do like to represent volumetric flow rate just as a terminology. It's just a notation. We do like to represent it as F. So simply we are saying that V dot is equal to F. It's just more beautiful to look at things without dots. That's the whole story. And later at some other stage, we're going to tell you that M dot is equal to W. So sometimes it just makes our life easier to get rid of these dots. And then you're going to see at some other stage, you're going to tell you that N dot is equal to Q. So we are trying to get all these dots because these dots just confuse us when they are on the way. But not to confuse us a lot, we are going to take it one by one. So for M dot is equal to density multiplied by volumetric flow rate, and the volumetric flow rate is represented as F. So in this case, going a little smaller, okay, so this will be rho N Fn minus rho F. Beautiful. To continue, so here we have the multiplication of three different variables. And if you can recall, if we have a differential equation of x and y by dt, this is equal to x into dy by dt. That's the product rule, plus y into dx by dt. In this case, definitely a is constant, so we are going to get rid of that, and get rid of it to be out of that equation, and we're going to have rho into height. And I would say that it's a good assumption to say that density is constant. I think it's a good assumption to say that density is constant for liquid systems. In specific, that the temperatures are usually under control for reaction. So, and another reason is that temperatures are under control for CSTRs. So in this case, we are saying that a density, keeping it as a constant, is also a good assumption. So we can take both density and area out of the term. So and just to recall as a part of remembering, what we're trying to say here, actually we are not taking it out of the term. We are doing this product rule. But because one of them is constant, and if we say, for example, x was the one which is constant, so d a constant value by dt, because d of a constant value is 0, which means dx by dt, difference in x is a constant, so there's no difference, so it will be 0. And this is why it looks like here, if this drops out of the term, it will look like exactly like this x is going out. You see, that it is out here. So we are applying the product rule. I'm just saying that just to feel comfortable that we're not doing something different. Okay, great. So recalling, dm by dt is equal to input flow rate m dot minus m dot, and then we substituted m rho a into h is equal to density into the volumetric flow rate. So that was density into volume. Here we have density into the volumetric flow rate. They are different. This is mass and this is mass flow rate. So mass flow rate will be density into volumetric flow rate minus density into volumetric flow rate, input minus output. And this is telling that how much is entering the tank. So how does the height or how does the mass change here? The mass changes in the tank depending on how much is entering per time minus how much is exiting per time. If there's more in, this will accumulate and it will go higher. If there's more out per time, then this will go lower, and of course the level of the tank will go lower because we have more output. And I will represent that with the example. If you have a roundabout, and if you just think of a roundabout of I'll try to make my drawing looking much better. Okay, that seems good. I didn't expect that for myself. Okay, so if you have a car coming in into this roundabout, and this is a car coming out, and this is car, these are just cars coming in on the way. So you have more cars getting in than getting out, so you have a long queue of cars. But if the cars are actually getting out really quickly, more than the one getting in, beautiful. So you'll have no cars in, you're just having no accumulation. So simply you will have accumulation when you have more input than output. Okay, so that's what we are trying to say. If you have more input than output, you will have accumulation. Okay, so we have dm by dt is equal to m in dot minus m dot. We substituted m, rho into volume, and volume is a, into height, is equal to mass flow rate n, which is density into volumetric flow rate minus density into volumetric flow rate. So let's continue. This will be now like rho a, which are constants, into 2dh by dt is equal to rho n fn minus rho f. Well, now if you can see here, we have rho n and rho. Are they the same terms? Okay. Well, density of what's getting in could be different from the density leaving out the system, especially that I'm having a reaction here. Even if I don't have reaction, I'm still having, like, if it could be more than one liquid, A or B or whatever, things could be changing. And actually it is a good assumption to consider that they are constant, especially they are liquid system. There is a difference, but the difference is very small. It's not that much to bother about, especially when you talk about process control later. That small differences are negligible, or they are not of a concern at all. So simply what we are trying to say here, we are trying to say that rho n is equal to rho. Okay, so this system will be looking like rho a dh by dt is equal to rho n fn. Sorry, we don't want rho n, so that will be rho fn minus rho f. I'll keep it rho n, maybe it just makes you comfortable, and we just understand that they are already constant values. So what we'll have here, we're going to cancel out the rho terms, and the system will be something like that. The height in the system will change depending on the flow rate getting in and out. And here if you look at fn, this is fn getting in, and actually fn in this system will depend on a pump. Okay, will depend on the pump that is pumping in. So it depends on the pumping power that is trying to push on liquid into the system. However, if you look at the output flow rate that is leaving the system, that will depend on what? This is the output flow rate that is leaving the system. It will depend on what? It will depend on the height, the head pressure. And we will say that if you have a higher level, you will have more flow rate flowing out. And if you have a lower level, it will be less flow rate. And this looks exactly like what you have. For example, I will always like the example of a Vimto. So I'll make a very strange kind of a tank. I don't know if this looks good. Okay, I don't know how that looks like. Whatever, you go in a swimming pool, enjoying your time in a very sunny day. Oh my God, that's really hot. And then you come out here. Here, I want to have some kind of to drink, please. And you have the tank here, and you come and pour your glass. My glass is not that good. Okay, that's fine. Small glass, drink that beautiful Vimto and that very sunny day. Okay, so you're drinking that kind of Vimto. You're really happy guy here, feeling cool now rather than feeling red or feeling blue. Beautiful. That's the first guy. And he's really having a very good output flow rate here. Output flow rate because the height of the Vimto is really high. But the next guy, and the third guy, the fourth guy, they come on here and the last one who comes out of the pool. The last one comes out of the pool. This is very low. And because it's very low, he's trying to get some kind of liquid out, but it's very low. Why? Because the head pressure is very low. So you really cannot get anything out of there. I think you need all your friends to push this tank so that you can get something out. So what I'm trying to say here simply is that if you have a higher head pressure, definitely you're going to have something out. So here we are saying that the flow rate in the example here, this flow rate that we have here, it depends on what? It depends on the head pressure. Actually, it doesn't only depend on the head pressure. It depends on an equation. And this equation could be represented as following. And this is like F is equal to alpha. Just to remove the sun from the way. Sorry for that. F is equal to alpha square root of h is the simple term that you will find in your book. So F is equal to alpha square root of h, and that is good enough for you to go on and solve your problems. And where does that come from? Actually, it comes from the equation, which is that alpha is equal to the square root of the delta P over the specific gravity multiplied by a term that is related to the valve. And if you look at these terms here, we know that delta P is equal to rho GH. So this is equal to CV into square root of rho G into square root of H over square root of specific gravity. And all these terms, you consider them as alpha. So that will be like alpha square root of H. Beautiful. So this is what we have. So if we turn to our equation here, we have dH by dt is equal to Fn. It will be identified by the power of the pump minus alpha square root of H. And that is our beautiful equation here of how does height change with time. Beautiful, very beautiful. So this is how does height change with time. And talking about how does height change with time, it means that my height will depend on the input flow rate, and it will depend on the function of the valve. It will depend on the opening of the valve, the characteristics of the valve, and it will also depend on the height. Actually, this alpha is not only the characteristics of the valve, it also depends on the density of the valve and so on, and the height term. And this is how to know how does height change with time. Very beautiful, very beautifully represented. We have an equation, and this equation of course can be solved by different means. We can solve this equation by many different means. We can solve it by taking direct solving any differential equation, dealing with any mechanistic form of a model. So just direct integration to solve a problem, or we can do some kind of linearization and take it to another space, or sorry, another dimension, and this other dimension we call it, there are many other dimensions by the way, but this dimension is Laplace, and we get something called transfer functions. Or we can solve it through taking it to another dimension called the state space. So this is like a matrix dimension, if I would call it. It's a matrix dimension. Beautiful. So talking about the integrations like the t dimension, I think so it's nice to put that in a different color. So this is like, I think so I have already used blue. So whatever else I will use, I got a green. Okay, so that is like the t dimension. Okay, and the transfer function is the s dimension. And I already mentioned that this is the matrix dimension. And each of them have advantages and disadvantages to solve this differential equation. Okay, so this is about solving the differential equation, but our aim today is to know how to develop the model equations, and this is how to develop the model equations. We got dH by dt is equal to fi minus alpha square root of h. So that was our goal here. Beautiful. After achieving our goal for dH by dt, if you just can recall, we wanted to find dH by dt, we also wanted to find dC by dt, and we wanted to find dt by dt. So these are like three different terms we want to find for the CSTR reactor. We already found how does height change with time. So we need to work on the rest. But we are not going to do in this lecture. We are going to do something additional before getting into the details of the next lecture by finding dC by dt and dt by dt. We just want to know, can this problem, okay, I'm going to write that, can this model equation be solved or not? So if you put this, okay, what happened to my not or not? So if you put this into Simulink or MATLAB, whatever, in a simulation platform, so if you put it in a simulation platform, can it be solved or not? Can this equation be solved or not? This equation, I'm going to write it again. So dH by dt is equal to fi minus alpha square root of h. So can this equation be solved or not? A good question. And to do this, we need to run a degree of freedom analysis. And let's do this degree of freedom analysis. Doing a degree of freedom, okay, sorry. So doing a degree of freedom what do we need? We need to remember the following. I like to call it the VIP, degree of freedom analysis. So the variables, V stands for variables, so I'll write that here. So V stands for variables, and I stands for inputs, and P for parameters. So what we have variables? For variables, we have things that we call them state variables. And variables also could be normal variables. And we're going to say what are the differences between all those. And actually, the inputs itself, the inputs themselves could also be considered as variables, but we like to separate them. And the reasons that we separate them is that they do not appear like they are a variable, because they could kept as a constant value that you just control. So usually this does not change, the input does not change with the change of the conditions. We are going to understand that in a moment. Well, let's look at the state variables and the normal variables. Okay, so the state variables are simply the differential equation, the term in the differential equation. Okay, so if you go back to our equation, this is our equation here. So what is the term that is in the differential equation? It is the height. Beautiful. That's all. The dH by dt. So it's the only differential equation here. And if you go now to the normal variables, what do I have as a normal variable here? Actually, alpha is a constant. Alpha is a constant. So because alpha is a constant, parameters do mean constant values. And we said alpha is constant because it's a function of specific gravity and the CV with the characteristics of the valve. And it's either that I'm going to give you the values of CV and so on, or most probably I'm going to tell you alpha is equal to 0.9 and that's all. So I'm going to give you the value of that constant. So that is a constant. And if you go to the inputs, so we have the input here in this case is only Fn, which is the flow rate n, which depends on the power of the pump. So if you look at what are what do I have in this equation? I have H, I have Fi, and I have alpha. That's all. This is what I have, and we can see all of them are appearing here, and that's all. So we don't have really other normal variables in this case. In this case, we don't have one. Actually, if we did not substitute F is equal to alpha square root of H, if you can remember and recall that we said that this F here, F is equal to alpha square root of H. If we did not do that, then we could consider that it is a variable that we can add as a normal variable, and we have another equation for it. So talking about this case that we have here, how many equations and how many unknowns do we have? So if, the degree of freedom says that degree of freedom is equal to mv minus number of equations. How many variables do I have? I have just one variable, v, just one variable, minus one. How many equations do I have? I have only one equation here. So this is 1 minus 1 is equal to 0. So it is exactly specified. Beautiful. So that is exactly specified. Of course, it could be over specified if it's greater than 1, or it could be under specified. Or I think so the other way around. It's greater than 1 is under specified, or less than 1 is over specified. But in this case, we have it is exactly specified. Just to repeat what we have, repeat it in a sense that instead of I would say that I did not submit F is equal to alpha square root of H. So what equations do I have? I have two equations, which is dH by dt is equal to Fi minus alpha square root H, and the other Fi minus F, and the other equation says F is equal to alpha square root of H. So here I have two equations, and if I want to apply now the degree of freedom, where I have my VIP, and here I have state variables. As the state variable I have H, and for the normal variable I do have F, and for my input I do have Fi, and for my parameter I have alpha. And if I will calculate this, my degree of freedom is equal to NV minus NE. This is equal to, I have two variables, 2 minus 2 equations, as I can see here, minus 2 is equal to 0. Exactly what we have obtained for our equation, exactly specified. Great. So what we have taken so far today, we have taken so far today how to model the equation. I'll do that slowly. Let me open it a little bit. Beautiful. Little more. Okay, so what do I have here? I have a system. Either see the cursor. So I have a system here, and in this system you can see I have a CSTR. So what we are trying to do today, we are trying to develop the model equations of a CSTR. So yes, we are developing the model equation of the CSTR. If we only ask, or your goal, I mean ask in the exam, or your goal is to find how does height change with time, then what we have done is good enough. But usually for a CSTR, height is not our only goal, temperature is also another goal, and the concentrations is also another goal. So what we have done, we finished with this. We are going to work on this. That will be lecture 4 and lecture 5. How did we find dH by dt? We found it through the overall mass balance equation. And after we found our equation here, this is our final equation, we have run our degree of freedom of how to find it, how to find that this problem can be solved or not, and we found it to be 0, and it is exactly specified. So this is how to develop the model equations to find how does the level or the height of a tank change with time. And next lecture we're going to take how does temperature and concentration do change with time. Thank you very much. I hope that you have gained a lot from what we have taken today. Thank you very much.